In Lab 2, you're going to have to run two different kinds of simulations, one with wall resolved mesh and one with wall modeled mesh. And I talked about this in training session 5, where we basically said that, um, well, instead of using very, very thin layers of cells to mesh the boundary layer, we can actually use one big cell to model the behavior of the boundary layer using experimental results. And we call this a wall modeled approach compared to a wall resolved approach. So again, the whole point of this is to simplify our computational setup and use experiment results or other kind of results to model the flow physics of the boundary layer instead of actually directly calculating it. And in lab 2, you're going to do that for the flow around the cylinder, and you're going to investigate what kind of effect or changes in the results appear. And I also mentioned or talked about how we sort of talk about these the mesh, it's the cell near the wall, because depending on the height of the first cell, that really changes how our that really changes how things are calculated. So we introduce a dimensionless parameter called y plus, and y plus represents the distance between the wall and the centroid of the local cell. So think of this as a dimensionless parameter that's related to, for instance, this distance here from the wall to the centroid of the cell. So a larger y plus means you have a taller cell, whereas a smaller y plus means you have a very short cell down here. Okay, and this is only talking about the first cell next to the wall. We also introduce another dimensionless parameter called u plus, and this is a dimensionless velocity of that cell. So instead of using simple y, so the actual distance and the actual velocity in that cell, you are using non-dimensional versions of them called y plus that represents the distance of the height, and u plus that represents the velocity of inside that cell. And we find a relationship that when y plus is smaller than 5, so when you have a relatively thin first layer height, the u plus actually has a very linear one-to-one value to the actual y plus. So that would be in this region here called the viscous sublayer. And you can see that this is a log scale. So this is 0.1. This green line here, that's 5. So when you're between 0 and 5 for your y plus value, it turns out that the u plus is actually very well aligned with y plus. So we have a linear relationship between u plus and y plus. So that makes things very easy to model. So if your y plus is below 5, you can, instead of calculating the physics here using the whatever governing equations you have, you can simply apply a u plus equals y plus relationship and then calculate the flow field like that. It saves you a lot of computation time. Interestingly also, when the y plus value is between 30 and around 200, which is from this green line to this green line, and we call that the log law region, we see this relationship where u plus is a function of the log of y plus. And what that means is this blue line here, it looks like a linear line here, but because we're in a log scale, this is a log relationship. And we see that the u plus agrees well with some function of log y plus. So again, if our y plus is a bit bigger than 5, so between 30 and 200, we can use this relationship to calculate or to figure out what the flow should be here without having to solve the governing equations directly. And then we have y plus regions between 5 and 30, where the relationship between u plus and y plus is a little bit murky. So this red curve here is a little bit difficult to define. So we call this the buffer layer. So when we do wall modeling, we generally try to avoid avoid having y pluses of between 5 and 30 because it's a bit difficult to define the relationship between u plus and y plus. In other words, it's difficult to define the flow field, which is characterized by u plus, only based on y plus. Okay, so in practice, when you want to have a wall resolved mesh where you want to say that you have a very nicely meshed boundary layer and you're just going to calculate everything, you generally want to have your y plus to be around 1, and we call that well resolved. So if we are to compare wall resolved cases versus a wall modeled case, in actual implementation, we're talking about comparing meshes with a y plus of 1 versus some other y plus maybe around 30 and above and using a wall model and comparing those results. Okay, so let me actually open up the demo case that we gave you. And this is the case that I showed before, where I've already ran it to 5 seconds. So this is the demo case, and I told you that the demo case has a average y plus value of around 38, I think it was, and that it has wall function enabled. So let me just try and open up. Give me 1 second. Okay, so here is the case file, and I can actually toggle the y plus, and I can look at the y plus around our cylinder. Let me also change this to surface with edges, and as you can see, our first layer cell is very tall. We're trying to capture the entire boundary layer just using this one cell. Let me also change the color map a little bit, just to make it easier to see. I think this will be good. And I'm going to change the range from 5 to 30. Okay, the reason I'm doing that is because if our y plus is below 5, in which case it'll just be black, we know that that's a good value to use a wall model. Similarly, with above 30, it'll be just grayed, and that tells us that that's a good y plus value to use a wall model. Anything between 5 and 30 is probably not going to be so accurate to use a wall model. And as you can see, our y plus value is actually is a distribution around the cylinder. We have zones here where it's completely gray, which means it's above 30, and that's pretty good to use a wall model. We have zones here where it's completely black, so that'll be below 5, and that's also decent to use a wall model. But then we have these regions where it's a shade of blue, so it's between 5 and 30, where we go into that buffer region where the wall model may not be so applicable. So even if we have a y plus, an average y plus of, let's say, 38 around the cylinder, around the boundary of this cylinder, it'll be difficult to get every place between, that is a good y plus value for using the wall function. So when you do your analysis, when you run your simulations, it's important to check your y plus distribution around your cylinder and provide some kind of analysis, so be discussed some limitations, and your mesh is going to have to be improved iteratively. So your first attempt at making the mesh might actually not be very good. So you're going to have to monitor your y plus values, and you can monitor your y plus values by looking at your log file, right? So if you open up your log file at different time steps, it'll compute the y plus value. Let me just look for it. Y plus. Okay, so it tells you the y plus every few time steps. It tells you that along the patch wall, which we define as the wall of the cylinder, the y plus ranges from a minimum of 4.7 to a maximum of 73 with an average value of 34. That's an earlier time step. And at the very end, last time step, we have a minimum y plus of 3.9, maximum of 80, and average of 38. And that's what we are seeing here. The average y plus is 38, the maximum is 80, and the minimum is 3.9. But you can see that it's a distribution. If you were to make the mesh for y plus equals 1, like a wall resolved mesh, again, you will have a distribution of y pluses, and the idea is to try and get the average y plus to be around 1, but your minimum and your maximum, may be distributed between like 0 to 5, for example.